Mhm. Okay, great. It's great to be back. So this is part two of a sequence of talks on skein lasagna modules. Last time we introduced skein lasagna modules, which takes in an input link homology theory and yields a package of four manifold invariants. Today I'm going to specialize, well, in the second half of the talk at least, the input link homology theory to be Khovanov homology and its so-called knee deformation. And then I'll use that to, I'll explain a theorem of myself and my collaborator Mike Willis that uses those invariants to detect exotic four manifolds.
How good of a four manifold invariant is this, like relative to Donaldson invariant and so on?
I'm going to do a recap of some structures of the invariants. So let me begin the first half, which is more or less a recap of what was happening last time, and some expansion of an example. So recall that for any link homology theory, um, with some nice condition, a link homology theory is nothing but a functor from this cobordism category of links to the category of your chosen abelian category, say a category of vector spaces over a field. So here the objects are links. Let me actually impose framing condition, frame-oriented links in S3 and link cobordisms between them as morphisms. So link cobordisms again are surfaces embedded in an interval times S3 that co-bonds a link on the top and on the bottom. So given such a link homology theory with some mild additional properties, one can construct I guess for each pair XL of a four manifold X. So let me say, let me be careful and say compact oriented four manifold, and L is a framed oriented link on its boundary, the so-called skein lasagna module. Notation is the script S sub 0 upper Z, the input homology theory, XL. And this is roughly, so this is the vector space, if you like, spanned by so-called Lasagna fillings. Which are pairs of a skein and a decoration. Modulo some skein relations. And the picture here to keep in mind for this Lasagna filling is the following. So we have a four manifold X, possibly with some boundary, and possibly we have a link on the boundary, L. A Lasagna filling is some surface embedded in X outside some finite number of foibles that bounds the boundary link that was specified. Should think of some picture like this. This is my skein, and the decoration are some labels V1, tensor V2, etc. On in the homology of the links on those so-called input links. And I guess here, maybe since I'm orienting and framing everything, the sigma is taken to be framed. So this here framed refers to normally framed and oriented in a way compatible with the boundary data.
These decorations are elements of homology of some link that sits on the boundary of the
that's right. So in each on each of the input ball boundary of the input ball, we see a link Li. They are they have nothing to do with the boundary link on the boundary of X, and they are links inside S3. So I know I know what do we mean by taking its homology, and what do we mean by an element there. Right. And as a shorthand, just to make things simple, I think this is going to be the case for most of the things I'm going to say today. If my boundary link L is empty, I'm just going to drop it from the notation. So so your link homology theory might come with extra structures, for example, that of a grading. But whatever extra structures your link homology theory inherits, uh, your link homology theory persists, this will be inherited um, by the skein lasagna module. So I just say skein lasagna module inherits structures of Z, but it also has an extra structure which is a grading. Um, inside H2 of my manifold. So I guess I'm dropping the boundary link from this point on. This is referred to as the skein grading. So again, if you have a Lasagna fielding representing some element in the skein Lasagna module, the skein grading of that is just the second homology class represented by my surface. And you might complain there are some fourballs, but you can make sense of taking second homology class still. All right. I guess before going further, I really want to further expand on one of the example last time. And in the meantime, I will try to explain some very primitive notions in four-manifold topology. So recall that.
Sorry, if I drop the link in the boundary, would you then say that your invariant is
It's an invariant of the diffeomorphism type of my four-manifold.
But is it still vector space value, or is
Yeah.
it one-dimensional vector space?
It's still a vector space. It may very well be more than one dimensional.
What's it spanned by?
It's still spanned by such fieldings. You just erase this part from the picture. And surfaces in four manifolds can be very complicated. Well, the generators here are crazy. But after you mod out some skein relations, it's a priori very unclear what you get in the end. I will say at this point. I will, of course, present some non-trivial calculations we did in the case of Khovanov homology. But I guess that's as far as I can say right now. It can be zero, it can be one-dimensional, it can be infinite dimensional, and it can be anything in between, I guess. All right. So last time we considered this so-called boring functor, uh, denoted by H, or also known as the Khovanov-Rosansky GL1 homology. This functor, well, listening homology is assigning to every link the one-dimensional vector space. Um, but as Mina pointed out, there are actually slightly more structures than just this. In fact, this homology uh, has actual structure of a Z grading. So I'll put a Z grading here. So the target is actually Z-graded vector spaces and graded maps between them. Uh, and for a link, we are associating to it the one-dimensional vector space, but with grading concentrated in W of L, which is depending on your perspective, you can either say it's the right of this framed link L, or the maybe more intuitively the self-linking number. So how is this defined? Since my links are all framed, I can choose a framing direction and push my link off in that direction, and then I get a pushed off copy of L and L itself, and I can take the self-linking number of those two links. So this really means the self-linking number of L and push off of L in the using the framing. And for every cobordism um, between two framed links L0 and L1, you can check that if there's any framed cobordism between two framed links, then it must preserve the self-intersection number or the right. So the domain and target are actually one-dimensional vector spaces concentrated in the same grading. It still makes sense to say I'm sending any cobordism to the identity map. So this is still a very boring functor, but it's having this slightly more information than. Every cobordism will preserve the right because we are asking the morphisms to also be framed. So I guess it's a part of the condition here. So yeah.
Some easy example where the cobordism is not
Well, you take any cobordism. You can always frame a cobordism if you do not care what boundary condition it restricts to. You can always frame a cobordism and restrict the framing to the boundaries. But if you first fix the boundary conditions, you may not find one. I think the rise is a complete obstruction of finding a cobordism, framed cobordism. All right. So the claim is that the skein lasagna module with this boring homology as input of any full manifold, I can still understand this fairly explicitly. Namely, it is still the vector space generated by second homology classes of X, or stated more explicitly, for every class inside H2 of X, I get a generator I call x sub alpha. I take the span of all such generators. And the claim is that I get a canonical identification like this as z times h2x graded vector spaces. But I have to tell you what is the grading on the right-hand side. The left-hand side has a z grading inherited from my functor at h, and h2 grading, namely the skein grading. The right-hand side, on the other hand, I just declare the I call this z grading t grading. I just declare my generator x alpha to be graded to be homogeneous with grading the self intersection of alpha. I will get to this in a moment, and the skein grading alpha. So this is inside h2 of x. This is an integer, and here this dot is a pairing on h2 of a four manifold tensor itself to z. This is the so-called intersection pairing. If you like to think about this algebraically, this more or less comes from Poincare duality. For example, you can dualize to H upper 2 and take the cup product. If X has, well, let's say X is closed, then after you pass to H upper 2, you take the cup product, you land in H upper 4, and then you pair with a fundamental class. That can be one way of defining the intersection pairing. But as geometric topologists, I like to think about this geometrically, and this perspective will also be useful in explicit calculations. So let me just say for alpha beta inside h2 of x, represented by smoothly embedded surfaces, oriented surfaces, sigma 1 and sigma 2 inside X, closed. Actually, there are two gradings, but they are giving you they are giving you the same information, so I'm dropping one of them. But both the homological grading and the quantum grading should give you the same information.
Actually, who wrote down the CL1 theory?
I think if you want to find a place, you might be able to find it in, but this is certainly not going to be the first reference. But this GL1 theory in the context of skein-skein modules was written down in more recent Walker and Baldrick in 24, I think. And I'm kind of adjusting their presentation a little bit and give you the version here. All right, so if I have two homology classes, I can represent them by closed oriented surfaces inside my manifold, and I can assume by general position that they are transverse to each other. Then the pairing between the two classes alpha and beta is nothing but a signed count of the intersection between the two surfaces. So this is a zero manifold, and you can count with signs. You get an integer. All right, I want to briefly explain how you get this interesting number, self-intersection number from the definition. So so last time we roughly explained that for 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 this canonical class X alpha, um, in the skein lasagna module, it's roughly represented by some surface with class alpha with some boring decoration. But that's not entirely precise if we want to take the framing into consideration. The problem is that so uh, let's take any class. Um, so we want to represent X alpha well by some Lasagna filling. We also take take a surface. We want to represent X alpha by some Lasagna filling where I more or less want to say the skein is just this surface here, and the decoration is one in my base field. But what's that?
Alpha is a homology class.
Yeah, yeah.
Your schemes have no more information about the surface than its homology class.
Well, so that's the issue here. This sentence that's written is not correct, and the issue lies in the fact that well, it's true that you can represent every homology class by a smoothly embedded surface, but this surface is not going to be framed a priori. You may not be able to frame a surface, and I'm going to explain this issue and how the self-intersection number comes in.
But I imagine that there are many more surfaces than those. In other words, your invariant does it only does it only depend on the surface of the its homology class, or it's not about the actual surface it's inviting now?
It only depends on the homology class.
But this is for GL1.
Yeah.
GL1.
Yeah. That's right. Okay. The issue again, sigma may not have a normal framing. So if we look at this more closely, we should realize that we should look at a neighborhood, a turbulent neighborhood. Of sigma denoted by nu of sigma. This is it's a disk bundle, D2 bundle over the base sigma. And disk bundles over a surface is classified by the so-called owner number. Or if you like, it's in this dimension, it's equivalent to the first Chen number. Which is an integer inside, which is an integer. And this bundle is sigma admits a normal framing if and only if this bundle is trivial, because normal framing is saying that you can find a section, non-vanishing section of this bundle. So we can frame sigma if and only if this obstruction vanishes. But in general, this may not be the case. Well, by the way, how to define this owner number in a geometric way?
Actually, before you go there, so what's the nature of this field on theory? Are there some, like, if I give you a link, does it produce the chain complex or just spits out a vector?
It gives you a chain complex of one term, which
which
is the same as a vector space. Yes. So in general, when the owner number is non-zero,
so sorry, now what's the signal?
oh yeah, sorry. So sigma is a surface inside. Yeah, this is a trivial neighborhood of sigma, or you can also think of it as a normal bound. And it's this bundle is classified by the owner number, which I'm going to redefine if you don't know that. So one can, in general, one may not be able to take a non-vanishing section of this normal bundle, but in any case, we can perturb my sigma a little bit to some sigma prime, which I can think of it as still sitting inside this trivial neighborhood or the normal bundle, if you like, such that sigma and sigma prime intersects transversely. Then this normal owner number is nothing but the signed count of the intersections between sigma and sigma prime. But in fact, you can do slightly better than that. Namely, we can assume we can push all the intersections into a local region. Can assume the intersection between sigma and sigma prime is contained in some D inside sigma. So this D, where this D is a local disk, just a disk. So I'm going to draw a picture for this. So, it's a toy picture. You have your surface sigma here, and you try to perturb it a bit, and you can actually perturb it so that over most points in the surface, except a very small region, the perturbation is actually disjoint from my surface. But in a small region right here, let me try if I can draw this picture. You see some geometric intersections. Here, maybe you see 3 intersection points in a local disk. This blue is my sigma prime. Now that all the intersections are contained in a local region, what we can do is we can then delete a four-ball B out of containing D out of X. So this four-ball, if you like, is just something like that. So after I delete this four-ball, everything outside just looks very nice. like this. So this is sigma outside the four ball. This is sigma prime outside the four ball, and very importantly, they have no intersection. So this picture illustrates the fact that sigma indeed four ball can be framed. Well, or is framed by sigma prime indeed the four ball. Hence, this is a skein. And then with actually it is a skein with input link being the unknown.
So the framing is just a vector at every point of the surface, left or not, right?
For knot or link, the framing is a nowhere vanishing vector in the normal direction, and for the surface, it's exactly the same. Mm, yeah.
So does this give you some formalized version of Donaldson theory?
I don't think so. No. Yeah, I don't see a direct relation between this and Donaldson theory. I will mention Donaldson theory very briefly in a bit. Okay, but okay, sorry. This boring homology theory is not going to detect exotica in any case. It's just something algebraic. But if you change the homology theory to Khovanov homology, the claim is that it does detect exotica. Right, in terms of definitions, it's certainly much simpler than the gauge theoretic invariants. Well, now the upshot is that I can represent this distinguished class X alpha by sigma delete the four ball still with label 1, but this is now inside the homology of this unknown. But homology of this unknown is a one-dimensional vector space concentrated in degree the self-intersection number of this unknown. But when I say it's an unknown, I didn't imply that the framing is the zero, is the trivial one, but rather, if you look at that picture over there, you can realize that the self-linking number of this unknown with a push off of it, given by the boundary of this blue surface here, is.
You don't know that this isn't some U1 gauge theory. Donaldson theory is like a U1 plus 1 hypermultiple, so it's there's stuff inside. But this could be just you could get this from just U1 gauge. I mean, in particular, the fact that all the invariants just correspond to self-intersection something. That's the only thing that a U1 theory knows about self-intersection. I mean, intersections occur. Like intersection number is the only thing that we actually know about. So with some heavy defect, I think.
I think the most different part is that this invariant assigns vector spaces to full manifolds rather than numbers.
I mean, but the vector space is so yes, but I could tell you, I take a U1 gauge theory, then I pick a homology class inside the surface, and I give you an invariant. And here it becomes a vector space value because, well, it's not just four manifold plus a homology class. Wouldn't that look the same? Just something that associates a number to a four manifold.
You may not be able to extract a number a priori because for more complicated input homology theory, you might get infinite dimensions in every gradient.
Yeah, no, I'm just talking about this one here.
Yeah, this one, probably there are some other explanations, but this example is fairly elementary. And I just want to illustrate some notions.
We're not all that dissimilar from the known theories, because the danger here is, to me, that this thing has nothing to do with this. In which case, to me, it would not be a good thing. So I'm hoping one can recognize something, that there's some way of looking at this thing where it's actually a familiar thing, as opposed to totally unfamiliar.
Okay, yeah, maybe we can see in the next part. The self-linking number between this unknown u and its pushed off copy u prime, you can actually calculate it by counting the intersection between so one way to define the linking number between two knots inside S3 is you take a surface capping off the first link inside the four-ball, and you take another surface inside the four-ball capping off the second knot component, and you take the intersection number between those two surfaces. Given that description, I can rewrite the self-linking number as the algebraic count between the intersection between sigma intersect B and sigma prime intersect B, which is the same as sigma intersects count of sigma intersects sigma prime, because every intersection is contained inside B. But this is exactly our owner number.
So U and U prime are links?
U and U prime are unknots. Unknots in the boundary of the input ball and
So you're just recovering the Gauss number from both dimensions.
So this roughly tells you why you get a map from, say, the right-hand side to the left-hand side. Well, a priori, you still have to show this is well-defined, meaning it's independent of the surface you are choosing, etc. But this roughly gives you that correspondence up there. Okay. Let me go to the second part, which is more four manifolds topology. And actually, maybe I'll put history here just to give you a sense of what people in this field who are working on, what are some important developments. So for four manifold topology, the most one of the most interesting questions is the discrepancy between diffeomorphism and homeomorphism. So as a first illustration, if you don't know this fact, a very good selling point for four manifold topology is the following. If you take the n-dimensional Euclidean space Rn, then it turns out that it admits a unique smooth structure if n is not equal to 4, while on the other hand, R4 has uncountably many distinct smooth structures. So this is, I guess, one of the first indication why dimension 4 is interesting for such kind of questions. And maybe to put things more generally, for any dimension, so let's say we fix a dimension n, we can consider two different set of objects. One is we study for smooth n-dimensional manifolds up to diffeomorphisms. The other is I study just purely topological n-manifolds up to homeomorphisms. And certainly there is a forgetful map that you can go between them, take a smooth manifold, forget about its smooth structure, then you land in the world of topological manifolds. So I denote this forgetful map U of n. Then it turns out that by some very, very explicit smoothing argument, UN turns out to be an isomorphism for n less or equal than 3. As dimension is small enough, you don't see any discrepancy between those two different categories. But in general, but for n greater or equal than 4, UN is neither injective nor surjective. However, the failure of the injectivity and surjectivity can be studied. I'll just say algebraically. When the dimension is greater or equal than 5. So that's essentially the reason why dimension 4. It's by some surgery theory techniques. I'll just put surgery theory, which I don't understand very well myself, so I'll not say much. But maybe one keyword is the H-Coborizan theorem, or the more generally the S-Coborizan theorem, if you are interested. Very importantly, this is a theorem that holds for manifolds with dimension at least 5. In dimension 4, it fails quite miserably. So this is really the reason why 4 manifolds are of its unique interest to topologists. I guess those two statements before 1980s are roughly what we knew about the comparison between those two categories. And greater or equal to 5 was more or less due to Smell, who proved the H-Coborizan theorem, which later was enhanced to this S-Coborizan theorem. But for n equals to 4, this is actually a very intricate question until the appearance of Simon Donaldson and Mike Friedman. So the failure of U4 being injective or surjective follows from just say deep results of Simon Donaldson and Mike Friedman. So to give you slightly more context, let's say I'll just give some examples to illustrate the issue here. So suppose X is a closed topological full manifold. Let's also say it is simply connected. The fundamental group is trivial. Then one very useful invariance beyond the homology groups is the so-called intersection pairing, which we already introduced a while ago. But let me give you a notation. The intersection pairing Q of X is a symmetric unimodular pairing. Unimodular just means if you write it in terms of a matrix, then the determinant is plus minus 1. For example, when X is equal to CP2, the second homology is just Z, and the pairing is given by the matrix 1, because CP1 has self-intersection number 1. And if you take, for example, S2 times S2, then the self-intersection pairing is 0, 1, 1, 0. The two generators for H2 are the first H2 factor and the second S2 factor. They each have 0 self-intersections, but they pair, they intersect once with each other. Let's see. I think I can give a non-trivial example. If X is the K3 surface, then the intersection form is, I hope I can remember this right, 2 times the E8 matrix plus 3 times this matrix here. Maybe the minus E8 matrix. Okay. And what Friedman showed is the following very clean, you can say, classification of topological manifolds, four manifolds that are simply connected. And I guess for simplicity, I'm not going to state the full version of it, but let me say that every symmetric unimodular form is represented by some topological form manifold for some closed, simply connected topological form manifold. Algebraically, whatever form you can come up for me, I can hand you a topological form manifold realizing that form. And secondly, if x1 and x2 are closed, simply connected smooth form manifolds with the same intersection form. then they are actually homeomorphic. Note that a priori, one may not be able to realize a given symmetric unimodular form by a smooth form manifold. But once you land in the world of smooth form manifold, then up to homeomorphism, this is the only information more other than the fundamental group. Well, if you land in simply connected smooth form manifolds world, then this is the only information you get for manifolds up to homeomorphism.
And you prove this just like straight topology, no gauge theory, nothing.
Yes, but this is a very hard theorem, and I don't think I can say much about it. Yes. On the other hand, we know already from earlier work of Roquelin, 52, that if X is a closed, simply connected smooth form manifold with intersection form even, here the even condition means just means that if you take any class alpha, pair it with itself, this is even. Then we have a fairly good constraint on the intersection form, namely its signature is divisible by 16. On the other hand,
sorry, Q isn't always even?
this may not, so for the example here, this form is not even because the generator pairs to 1 with itself. This form here is even because.
I mean, isn't it trivially even, like the way X?
So if you take, for example, E1 plus E2, and pair it with itself, you are going to get 2E1 dot E2, which is 2. You cannot. Yeah. This is an even form. This is an odd form.
I thought you meant separate.
No. In this sense, in orange, then its signature is divisible by 16. But on the other hand, the E8 matrix is even with signature 8. So Friedman number 1 implies that there exist non-smoothable topological form manifolds. Smoothable topological form manifold with, say, intersection matrix E8. This is the so-called E8 manifold. And you can actually get much more than this by some other obstructions. Maybe I'll mention here this also follows. From the so-called diagonalization theorem of Donaldson. Which says that the signature, so you can say over the over the rails diagonalize your matrix. And then the signature is the number of positive eigenvalues minus the number of negative eigenvalues. The Donaldson's diagonalization theorem says that the same condition, X is closed, simply connected full manifold. Maybe, sorry, X smooth with plus the other conditions with QX positive definite. Then the intersection form is actually 1, 1, 1, 1, 1 diagonal, the same as that of connect sums of CP2s if you like. And again, the E8 matrix is a positive definite matrix, but it's certainly not a diagonal matrix. So this gives another proof that the E8 manifold is not smoothable.
Is it known what the E8 manifold is?
You can construct it by an infinite process of handled attachments, but I'm not sure if that's explicit enough description. You can write it down to some extent, but I don't think it's very explicit to me. Donaldson also showed also produced the following interesting invariants. I'll just say constructed a polynomial invariant. Uh-huh.
You know what that guy is?
Yeah, that is a that manifold. What I can say is that manifold has more than one smooth structure, but distinguished by the Donaldson invariant, which I'm about to get to. So Donaldson in 83 constructed a polynomial invariance for smooth, closed, simply connected, smooth for manifolds. Known as the Donaldson invariants. And he showed, for example, the invariant is non-trivial on K3. And in fact, for my purpose, I'm going to say K3 blow up once. But this is trivial. This is a very particular manifold. 3 copies of CP2 connect some 20 copies of CP2 bar. I call this X1, this X2. So this implies X1, X2 are not diffeomorphic. However, turns out that I chose those numbers so that the intersection forms of X1 and X2 are isomorphic. So Friedman number 2 implies that X1 and X2 are homeomorphic. So this shows the U4 map is not injective. This part shows the U4 map is not surjective. And both this Donaldson 83 and this Friedman 82 are fairly complicated theorems, especially Well, but well, I cannot say which one is more more complicated than the other, but Donaldson's theory is developed and modified by many other people throughout the recent 20, 30 years. Most importantly, there are similar constructions yielding smooth four-manifold invariants, for example, from Seiberg-Witten equations, yielding the so-called Seiberg-Witten invariants. And later, people have all kinds of Floer homologies. All those have something to do with Donaldson's original idea. But sorry, give me a sec. I guess that's so far for the format for introduction, and as a terminology, people usually call such pair of x1, x2 an exotic pair. And in the rest of today's talk, I'm going to present our way of detecting exotica using skein assignment modules. By the way, do people need a break? Do we usually have a break? Okay. Then I just. Okay, I think I'm fine. Let's keep on going. So let me state the mean theorem of our earlier paper. But before doing that, since this is not a topology seminar, I think I'm going to introduce some simple ways of constructing four manifolds. Then I can state my mean theorems without ambiguity. So going to tell you some simple ways to construct four manifolds from knots. So let's say we have a knot K inside S3. And let's say we have an integer n. Then from those two data, I can construct the so-called n trace on K.
Is it that you can get any four manifold
No, not necessarily. But this will be the four manifolds of our interest.
For example, those K3.
You can get the K3. You can get all those three examples in a way similar to this, but not every four manifold. The n trace on K is the smooth four manifold denoted x n of K, obtained by you start with a four ball and you attach a two handle, four-dimensional two handle along a knot K with framing n. I'm going to explain this in more details. So what does this mean? Maybe I'll also draw a picture. Take the four ball. You take a knot on the boundary K. Attach a two handle like this. But what this means? Well, a two handle. You can just think of it as B2 times B2, where the boundary of the two handle is divided into two halves, namely S1 times B2 and B2 times S1. So in this picture, one of those pieces is the green piece here. The other piece is the red piece here. And the gluing, the union over there, is taken along the first copy as 1 times B2 in the boundary of the 2 handle. And this is group 2, a turbulent neighborhood. Well, I'll just write S1 times B2 inside S3, which is the boundary of the 4 ball, given specified by the link, by the knot.
So this guy still has a boundary off that back, right?
Yes, that's right. If you take a turbulent neighborhood of your knot, you get a solid torus, which is an S1 times B2. If you also take the framing into consideration, you get a canonical way to identify that turbulent neighborhood of with this solid torus. And I grew the two pieces together by identifying this solid torus with that solid torus. So then one can see that homotopically this knot trace is just if you forget about some thickening dimensions, then it's actually homotopy equivalent to a point union a 2 cell, which is S2. So this notation is homotopy equivalence. So in particular, we have, for example, fundamental group is trivial, and H2 is Z. And we can also see that the intersection pairing is a one by one matrix given by the framing. And I don't think I have enough time to explain why that is the case, but more or less you can see what is a generator for the H2 here, and more or less you can realize the generator by taking a copy of B2 times a point and some surface capping off my knot in the interior. And you try to push it off and count intersections. And some framing condition tells you that the intersection is exactly this number n. So this gives you some interesting class of four manifolds, and in terms of handle decompositions, they are as easy as you like. They consist of only two handles, one zero index 0 handle and one index 2 handle. So they are among right. So right, you can shrink the B4 to a point, and you can shrink the attaching region to a circle, to S1. So
so when you shrink B4 to a point, haven't you shrunk the attaching region
or maybe I should say you shrink the 2 handle to B2. You crash one of the direction, then yeah, one has to be careful about this. This can be done. For those class of four manifolds, I guess for precision, or really this is a coronary of Friedman, not the theorem I stated above, but a coronary of his paper or some slight generalization of something there tells you that if the Fermi n is plus or minus 1,
Sorry, I thought Friedman have compact format.
right, it's not exactly the theorem I stated above. It's a coronary of some other results in his paper. Right, this manifold will have boundary. That's very important. But if so if my Fermi coefficient is plus or minus 1, k prime naught with boundary of the n trace on k homeomorphic or diffeomorphic, it doesn't matter. This is the 3 manifold. Homeo or diffeo agrees here. If those two 3 manifolds, those two boundary 3 manifolds are equal, then actually the two knot traces are homeomorphic. So we've seen that in terms of the algebraic data, you don't see too much. You only see this Fermi n here. This proposition tells you once you also get the boundary match well to each other, then you can deduce the homomorphism. And again, this is a very hard theorem. Let me try to state the exotic pair define our this will be useful. I guess I'll keep the pictures. This is a 5 or what? This is the other rhizome. This box here indicates twists. So -1 is the same as this right here. 94 is just 4 copies of that. Number 1, so this pair was actually not due to us. simpler proofs was also defined by using I guess side-written invariants plus some synthetic geometry. And later various floor homology. I guess maybe let's be explicit and say eager floor homology. So you can indeed prove those pairs are not diffeomorphic by fairly large amount of invariants that format of topologies are using. But all those invariants are very heavy in analysis, and our invariance, as you can see, is completely combinatorial. So this actually gives you the first proof of the existence of exotic four manifolds without gauge theory or floor theory. And second remark is that actually we can produce an infinite amount of examples.
I mean, we said that Khovanov mode is floor theory too.
Oh,
Don't think about it. Oh no, absolutely. That's a theory.
I don't think people have a consensus in that. I don't know. But yeah, I personally don't understand Newton's suggestion.
No, it's a different construction of Khovanov mode, which makes it a floor theory.
Okay, forget about that construction.
No, Witten's construction is not here.
But in addition to this example, actually we have an infinite family of examples of similar kinds, which and maybe I'll just say a priori it's not clear to me how to recover them from all these other methods. It does look to me that I cannot recover most of those examples. I just choose to present this pair because it's the simplest and I can join everything.
What is the family of examples you understand?
It's so
I rather maybe family of like in which setting you know how to compute this invariant. Or maybe you don't need to compute it to show that they're not the same.
Yeah. I'll show that in a bit. But let me focus on this pair because it's explicit on